Freeze a train as it moves to the right. The carriage is moving right. The axle is moving right. Most of each wheel is moving right. But this red point on the lower edge of the wheel is moving left relative to the rail. Not more slowly, not standing still, left. This is not the wagon wheel effect, and it is not a camera trick. It is what the wheel's geometry predicts. Start with an ordinary wheel rolling without slipping. Every point on it is doing two things at once. The axle carries the entire wheel forward. At the same time, the wheel rotates around that axle. Because the axle moves right, every point inherits that same motion to the right. Rotation then adds a second motion whose direction depends on where the point is. At the front, it points down. At the back, up. At the top, rotation points forward. At the bottom, backward. The strange part is not rotation. The strange part is what happens when we add it to the train's motion. The easiest way to combine those motions is to draw two arrows. Every point on the wheel gets the same arrow to the right because the axle carries the whole wheel forward. At the bottom, rotation adds an arrow to the left. For an ordinary wheel rolling cleanly, those two bottom arrows have exactly the same length. Put one against the other, and they cancel. That is why a bicycle can pass you while the exact point touching the road is, for one instant, stationary. At the top, the rotational arrow points right instead. Now the arrows add, so the top of the wheel moves twice as fast as the axle. Interesting, but not our answer. To make a point move backward, we do not need to reverse the wheel. We only need to make the left arrow longer. Move the red point a little farther from the axle, just beyond the edge the wheel rolls on. The wheel still turns through the same angle in the same time. But the red point now travels around a larger circle, so it covers more distance during that turn. Its motion from rotation is faster. When the point reaches the bottom, its left arrow is now longer than the common right arrow. Lay them on top of each other. The right arrow cancels most of the left one, but not all of it. A small arrow to the left remains. That point is moving backward relative to the ground. That is the whole proof. The same ride forward, but a longer sweep backward. Imagine a clear disc rolling along a narrow rail, with room beside the rail for a red pin fixed to the disc. Put the red mark exactly on the rolling edge. As the disc moves right, the mark traces a chain of arches. It moves forward, slows to a stop at the bottom, then moves forward again. Never backward. Now extend the pin slightly beyond that rolling edge and follow its tip. The path develops a small loop. Across the bottom of the loop, the red tip travels left while the disc's center continues right. No slow-motion camera is needed to establish the direction. Mark the tip's position in several successive snapshots, and the lower positions step to the left. The arrows predicted it. The traced path confirms it. Now look at a train wheel in cross-section. The tread rolls on top of the rail. On the inside is a raised lip called the flange. It helps keep the wheel set between the rails, and its tip reaches farther from the axle than the part rolling on the rail. The flange is not slicing through the rail. It runs beside the railhead, where there is room for its lower edge. So the wheel already contains the geometry of our red pin, a point beyond the rolling edge. Near the bottom, that point's sweep to the left can be larger than the axle's motion to the right. Cancel the two arrows, and the remaining motion points backward. Nothing on the train has changed direction. One small part of the wheel simply wins a very local argument between two motions. A real wheel and rail are messier than our clean drawing. Steel flexes slightly. Contact covers a small patch, and the effective rolling size changes with the wheel's position and profile. Traction, braking, and curves can also introduce a little slipping, so there is no single backward speed for every train, and not every flange point moves backward all the time. But the rule survives. Whenever a point's sweep backward from rotation is larger than the axle's motion forward, an observer beside the track sees that point moving backward. The exact amount belongs to engineering. The direction comes from the two arrows. So, Are parts of a moving train really going backward? Yes. In the ground frame, a point near the bottom of the flange can briefly move opposite the train, because rotation carries it backward faster than the axle carries it forward. The train does not reverse. The wheel does not reverse. One point traces a tiny loop while the axle carries the wheel down the track. The right arrow carries the wheel forward. The longer left arrow carries that point back. And the ordinary wheel, without any flange at all, still has its own quieter trick. The point touching the ground is standing still.